Chapter 2, Functions and their Graphs, Section 2.4, Functions. We begin by defining a relation between two variables x and y. A relation is any correspondence between the values of two variables x and y that can be described as a set of ordered pairs x, y. The set of all values of x is called the domain of the relation, and the set of all values of y is called the range. So the x's are domain values and the y's are range values. A function is a special type of relation in which each value of the domain corresponds to one and only one, and that's the key, one and only one value of the range. We have two relations diagrammed below. What distinguishes the function, the relation that's a function, from the relation that's not a function? That's the question we want to try to answer here. What we want to do is look at how the elements of set X are related to the elements of set Y. Note that for the first correspondence, correspondence that's diagrammed, element A corresponds to element 1 and only to element 1. Next element of set X, B, corresponds to 3 in set Y and only to 3. C corresponds also to 3, but only to 3. So B and C correspond to the same element of Y, but both B and C correspond only to that one element and not to more than one element. D corresponds to 4 and only 4. So for each element of set X, there's a correspondence to one and only one value in the set Y. So the first correspondence that's diagrammed is a function. We can represent that function as a set of ordered pairs. So if we call this function f, we could write f equals the set of ordered pairs a, 1, b, 3, c, 3, d, 4. We would then say that the domain, which we'll call D, is the set of all x coordinates of those ordered pairs. So that would be the set A, B, C, and D. The range, which we'll call R, would be the set of all y coordinates of the ordered pairs in our relation. So that would be the set 1, 3, and 4. And notice we don't include 2 because 2 did not correspond to any of the elements of set X, A, B, C, or D. So 2 is not included in the range of the function. Now let's look at the second correspondence. Why is that not a function? Well, let's take a look at each of the x's. A corresponds to 1 and only 1. That's okay. B corresponds to 1 and only 1. That's okay. A and B correspond to the same element in set Y, but that's acceptable as long as they only correspond to one element. The problem is with C. If we consider C, C corresponds to 2, but it also corresponds to 3. In other words, C is not related to one and only one element in the second set, Y. So this violates the definition of function, and therefore the second correspondence, although it is a relation between elements in two sets, it's not a function because of the relationship between C in the first set and 2 and 3 in the second set. Next, we introduce function notation. If the function diagrammed above is called f, then we may describe the relation between x and y by writing f of x equals y, which is red, f of x equals y. What we can do then is write the following. We can say f of a equals 1, f of b equals 3, f of c equals 3, and f of d equals 4. The element inside the parentheses is the x, and then that is equal to the corresponding y value. So for example, we have the ordered pair a comma 1. We're representing that ordered pair with a function notation in this fashion. The number inside the parentheses, or the element inside the parentheses if you want to treat it as just a general element, that's the x. And then the element that you set that equal to, in this case 1, that's the y value. So we very frequently will use function notation. We understand that the number inside the parentheses is the x, and the number we set it equal to is the y. So essentially we think of f of x itself. F of x itself is the y value. F of x is the y value. We can often define functions using equations. When an equation in x and y defines a function, we say y is a function of x and can write y equals f of x. For example, the equation y equals x squared can also be expressed as f of x equals x squared. Here x is called the independent variable, y is called the dependent variable. In other words, y depends on x. Notice how the notation f of x replaces the y when we write the equation using function notation. Some equations define y as a function of x, some do not. Those that do not are relations between x and y, but they're not functions. So we'd like to be able to distinguish an equation that defines a function from one that does not. Example 1 says, solve the equation for y. Does the equation define y as a function of x? If so, express the relation using function notation. So for part A, we're going to solve the equation for y by subtracting the absolute value of x from both sides. So we'll write y equals 1 minus the absolute value of x. Now, what we might want to do is just test this relation with a couple of values of x. For example, if x is equal to 0, then y is equal to 1 minus the absolute value of 0. The absolute value of 0 is 0, and 1 minus 0 is 1. What this is showing us is that for this specific value of x, there's one and only one y value associated with it, and that satisfies the definition of function. Suppose I chose x equals, say, -2. What would we get for y there? It would be 1 minus the absolute value of -2. Now be careful here. This is 1 minus +2. It's still a subtraction, but the absolute value of -2 is +2. There's no cancellation of the negative signs here. and that gives us negative 1. The main point, however, is that for x equal to negative 2, there's one and only one y value associated with it. So again, we see that the definition of function is satisfied, and pretty soon we would realize that it doesn't really matter what we choose for x. We're always going to get just one y value that corresponds to it. So does the equation define y as a function of x? The answer here is definitely a yes, and therefore we can write this in function notation, replacing y with f of x as f of x equals 1 minus the absolute value of x. What about the second equation, x squared plus y squared equals 1? Well, let's solve that for y. Subtracting x squared from both sides, we get y squared equals 1 minus x squared. To solve for y, we need to take the square root of both sides. Now, when I do that, it introduces a plus or minus sign in front of the radical on the right-hand side. This is the key step in what's going to follow in terms of this not being a function, as it turns out. So because y is being squared, we could take either the positive square root or the negative square root, and it would satisfy the equation. By the way, this is the equation of a circle, in case you're interested. It's a circle centered at the origin of radius 1. Perhaps you recognize it, perhaps you don't. That's not of any great significance right now. Let's choose a value of x, and a simple one to use would be x equal 0. If we substitute that into the equation, having solved for y, we get this. And if we simplify, on the right, it's plus or minus the square root of 1. Now the square root of 1 is 1. So we get plus or minus 1. In other words, if we have x equal to 0, there is a correspondence to both y equal to 1 and to y equal to negative 1. And as we showed above in the diagrams that we looked at, when an x corresponds to more than one value of y, then the definition of function is not satisfied. So this equation does not define y as a function of x. It is a relation between x and y, but it's not a function, and therefore it would not be appropriate to use function notation to describe the relationship between x and y.